Hey everyone, I hope you're doing well. This is Tony, and welcome back to the channel. So, in today's video, I wanted to briefly cover the concept of resonance, which is one of the most fundamental but also crucial concept in the course of organic chemistry because it helps us to predict the stability of structures, determine its reactivity, and also help with identifying the acidity or basicity of a compound, which will be mentioned in later chapters. Okay, so what's the objective of today's video? Well, I believe there are three main important ideas that are crucial to a lot of the future units in organic chemistry. And number one is to understand the concept of resonance, basically what it is, alongside with key principles related to resonance structures. Second is to identify and draw all different valid resonance structures by recognizing common molecular patterns in various molecular compounds. And third is to assess the stability of resonance structures and compare them to one another. First, let's briefly define what resonance is. So, resonance basically describes the delocalization of pi electrons or lone pairs across overlapping p orbitals. And if you aren't super familiar with the concept of orbitals or hybridization, I highly recommend looking back your general chemistry notes for a quick review. Additionally, the resonance structures we draw are actually not real isolated molecules, but instead tools used to describe and represent different electron arrangements. As illustrated in the diagram to the right, the true structure actually exists as a resonance hybrid with both partial charges and partial bond characteristics rather than full formal charges. Next, curved arrows are used to showcase electron movement in resonance structures and always start from electrons. Lastly, as a quick definition, allylic basically referred to the position one carbon away from double bond, which is a common setup where resonance can occur, and I will be briefly mentioning those later. Okay, so before moving on to the resonance patterns, it's important to first establish a few general rules that apply to nearly all resonance structures. First, resonance does not break any single bonds, as only electrons move. Additionally, atoms cannot violate the octet rule, meaning that they cannot exceed 8 valence electrons. Next, the overall charge of the molecule must remain the same. So, for instance, if a neutral molecule contains a positive formal charge in one of its resonance structures, there must also be a negative charge somewhere in the structure present to maintain that neutrality. Lastly, as mentioned previously, curved arrows are used to showcase electron movement and therefore must always start from a lone pair or pi electrons. Now, moving on to the actual bonding patterns, I decided to split the 5 patterns I know into 2 separate slides, with slide 1 demonstrating the more important ones and slide 2 with the less significant ones. So first is allylic lone pair, which as you may remember from an earlier slide, allylic just referred to the position 1 carbon away from a double bond. So as you can see in this diagram, the lone pair on the oxygen would be 1 carbon away from the double bond and therefore can produce a resonance. And how I like to remember this one is that it will require 2 arrows with the lone pair pushing down and then that pi bond of the double bond pushing out. Next is allylic carbocation with a similar idea of course, being 1 carbon away from the double bond. So as you see in the diagram, the carbocation would be 1 carbon away from the double bond. And in this case, it actually just requires 1 arrow with that push, which gives you the other resonance structure. Lastly is a lone pair adjacent to a carbocation. So as you can see here, the oxygen's lone pair would be 1 carbon away from that carbocation, and this one also just require 1 arrow for that resonance structure to form. With regard to the remaining 2 resonance patterns, however, their use can vary depending on the professor, so it's best to treat them with some caution. To start, the fourth pattern involves a pi bond between atoms of differing electronegativity, such as C double O bond or C double N bond. In this case, a single curved arrow is used to push the pi electrons toward the more electronegative atom, thereby also generating a carbocation on the carbon atom. However, this type of resonance introduces additional formal charges and is therefore a minor or negligible contributor when the molecule already carries an overall formal charge, as shown in the second image here. Lastly, conjugated pi bonds and benzene rings can also demonstrate resonance, But some professors choose to omit drawing these resonance forms since they represent the same structure, and instead depict benzene using a circle inside a hexagon to emphasize electron delocalization. After learning about the different kind of patterns, it's also crucial to compare different resonance structures and assess their stability. And how you exactly do that depends mainly on three different rules. So rule number one basically states that resonance structures with the greatest number of filled octet would be more stable. So as you can see in the image on the right, the second resonance would actually be more stable because the first one, with the carbocation only having 6 valence electron, it actually does not meet octet for every single atom, while the second one does. Rule number two basically states that resonance structures with fewer formal charges will be more stable. And as you can see in the example to the right, the left image would be a more stable resonance structure because it has no charge, while the right one will have two different formal charges. Lastly, rule 3 basically states that if the resonance structure have negative charge on the more electronegative atom and vice versa, so positive charge on the less electronegative atoms, that would be the more stable structure. So as you can see in the example to the right, image 1 on the left would be more stable because having a formal charge of a negative charge on the oxygen atom would be far more stable than having it on a carbon atom. It is also crucial to point out that these rules are only guidelines and are not absolute, because sometimes they can contradict with one another. For instance, if I try to apply rule number 3 onto the very first example, I might argue that the resonance on the left is actually the more major contributor because having a carbocation is far more stable than having a positive formal charge on such an electronegative atom like oxygen. But from my understanding, when resonance rules conflict, we usually prioritize the factor that most strongly stabilizes a molecule. And in these cases, it's usually rule number 1 because having a filled octet is more important for stability. However, there's always room for exceptions, as we'll see in a future practice problem later down the video. Last but not least, an important exception to highlight is that resonance can only occur when adjacent atoms have unhybridized p orbitals available for overlap. If this requirement is not met, resonance will not occur even if one of the 5 common resonance patterns appear to be present. As shown in the image to the right, although the nitrogen's lone pair is allylic to the adjacent pi bond, the nitrogen is already involved in the double bond itself, meaning that its lone pair resides in an sp2 hybrid orbital rather than the p orbital. As a result, proper p orbital overlap cannot occur and resonance is therefore not possible. Referring back to our previous definition, resonance requires the localizations of electrons across p orbitals, which is why examples like this do not exhibit true resonance. With this in mind, let's try to apply all the concepts and knowledge we learned in this video into the following two problems. So starting with number 1, the first recognized pattern you can observe here is that the lone pair on the nitrogen is actually allylic to that double bond, which is one of the 5 main patterns. And in this case, it requires a 2-arrow push to produce a second structure, as demonstrated here. So this will produce a second structure, and as you can see here, the formal charge of a negative charge was shifted from the nitrogen to the carbon, and the overall charge of -1 is still maintained. With this in mind, you can observe a similar pattern in which the lone pair here on carbon is again allylic to another double bond, which requires 2 more arrows. And the rule is present again with this lone pair being adjacent to that double bond. And last but not least, this lone pair on the carbon is now allylic to the double bond with the CN bond, and you can do another 2-arrow push. And that basically completes our resonance structures. And as you can see from all these 5, the most major contributor out of the 5 would be number 1 and number 5, because the negative formal charge is on the more electronegative atom, nitrogen, compared to carbon, which is more stable. Now, moving on to our second problem, we can observe two major patterns here. One is the allylic carbocation between this carbon and this pi bond, and the other one is adjacent lone pair on the nitrogen compared to that carbocation. So in this case, you can basically start with one of the two and just make sure to have an arrow pushing back to the original structure for the second structure to occur. So in this case, let's just start off with the adjacent lone pair on the nitrogen by using one arrow. As observed here as well, the total formal charge, which is +1 in this case, is maintained throughout all resonance structures because it doesn't change. Now, what we had to do, as mentioned earlier, is to use a arrow to push it back into the original structure, which is kind of basically how I think of it, a reverse arrow, and then using a new arrow to push that allylic pi bond. So looks something like this. And this will generate our third and last resonance structure. And in this case, the major contributor of the resonance is actually number 1 and number 3, even though the carbocation does not have a full octet. And this was briefly touched on earlier in the slide with the rules for stability, in which some case the rules might contradict with one another. And in this case, the main reason why 1 and 3 are actually more major is because having a carbocation is far more stable than having a positive charge on the nitrogen, which is more electronegative. All in all, this sums up the video for resonance. I really hope you guys enjoyed it, and let me know if you have more questions. Thank you so much, and I wish you the best of luck in all your studies.